Alright, so this next video will cover chapter 5, which is on graphs and graph theory. Alright, so let's get started then. So a graph. Right? So here, a graph is a set of points called vertices and line segments called edges. That connect the vertices. So we have vertices and we have edges. So for example, if I had some of this, so this is A, this is B, this is C, this is D, and this is E. And then I have my edges, and actually let's do those in different colors. And so A goes to B, B can go to C, B and D, A and C, E and D, and A and E. So my vertices are those black dots, and the edges are those segments that are in red. Right? So here again, my vertices are A, B, C, D, and E. And the edges connect the vertices. So then, given something like this, can we draw the graph that goes with the information? Draw the graph. That goes with the chart. And so we have, in terms of Matt, Amber, Oscar, Laura, and Kayla. And then here we have Matt, Amber, Oscar, Laura, Kayla. So we have this chart of, and now we'll fill in who is connected to who. So I'm finished making my grid here. Okay. And so we'll that. And we have Amber and Laura here. And then we have here. And then here and here. Oscar, Amber, and Kayla, Laura, and not here, and then Kayla here, and not there. So we have that chart. We want to take that chart and turn that into our graph. Right? So we're going to have Matt. We're going to have Amber. We'll have Oscar. We're going to have Laura. And we're going to have Kayla. So there's my vertices. So now let's draw in our edges. And so Matt is connected to Amber. And Matt is also connected to Laura. Okay. Matt and Amber we got. Amber is connected to Oscar. And Amber is also connected to Laura. Okay. Oscar and Amber are connected. We got that already. And Oscar is connected to Kayla. We get that. Okay. Laura is connected to Matt. We have that. Laura is connected to Amber. We have that. We have those already. And Kayla is connected to Oscar. We have that. So we have our graph that goes with that information. So we drew a graph that matches our chart. Okay. So if an edge begins and ends at the same vertex, it is called a loop. Okay. And a graph is called connected if any vertex if any vertex can be reached from any vertex by traveling along an edge. So a few examples here. So let's say I had this one, my vertices, and again, let's draw in our edges. So like this, have another one goes like this, and then this one goes like that, all right? So this graph is connected and has a loop. Right? And then my next example would be if I had something like this. And so now we have this. Right? And so this graph is not connected. Okay. All right. So it got connected and not connected, and whether or not it has a loop. Right? So then graphs are equivalent if they have the same edges connecting the vertices. So same edges connecting the vertices, and so example of that. So if I had this drawing, A, B, C, D, E, and so if I had this drawing, A to B, to here, to here, and to here, right? Or if I had this drawing, B, A, C, D, and E, right? And so these two would be equivalent, right? So they're both the same, just drawn out a little differently, but they are equivalent to each other. All right? So then we get a thing called a path. So path is a set of edges that leads from one vertex to another. And so, for example, if I had this, B, this is A, this is D, let's see, this is C, and again, I'm keeping with my colors. So I have that graph. And so I could have, in terms of this path, which has me going from A to B to A to C. That would be a path. And then if a path begins and ends at the same vertex, it is a circuit. And so here I could have from D to A to B to C to D would be a circuit. Well, then a circuit, so a circuit that uses every edge only once is called a Euler circuit. And so, for example, we have this drawing. So yeah, this is A, B, C, D, E, F, G, and H. And drawing all my edges. And so A to B to here to here. Up to here, here, and here. And then this one. And then that one. Right? So we have in terms of that drawing. And so my circuit here would be if I go from, for example, one of a circuit would be B to D to F to G to H to E to C to B to A to D to G to E to B. And we made a circuit. We left one place and we got back to the same spot. Right? Well, in terms of my vertices then, we can talk about the degree of the vertex. And the degree is given by the number of edges. And so, for example, if I had this drawing, and so this is A, this is B, this is C, this is D, this is E. And I can always draw in my edges. So here to here, back to there. This. So let's look in terms of my vertices and what is the degree of each. So we got A, we have B, we have C, we have D, and we have E. Right? So A, if I look at A, it has 1, 2, 3 edges. So this is going to be third degree. B has 2. C has 3. And then D has 2 and E has 2. So again, the degree is the number of edges that are attached to that vertex. Right? Some more definitions. And so a connected graph. Right? So a connected graph is Eulerian if and only if every vertex of the graph is evenly degree. And then there is a Euler path given you have a connected graph contains an Euler path if and only if the graph has two vertices of odd degree with all others all the other vertices are even degree. Okay. So, for example, then, if I had this graph, so A, B, C, D, E, and I can draw this in. So from here to here to here. And so if I look at this and I look at the degree of each of my vertices, well, A is 2, B is 1, 2, 3, B is 4, C is 4, D is 3, and E is 3. So it would have an Euler path because it has two odd degrees. And really what this means then is you can think of it as I could trace this out without lifting the pen. Off the paper. And so you could try that. You should be able to draw that figure out without having to have your pen leave the paper, right? And draw the incomplete figure, right? Without copying over any, right? Well, then, in terms of our graphs, there's some special types. And so the next one then is they talk about weighted graphs. And so you have in terms of Hamilton circuit, is a path that begins and ends at the same vertex. And passes through each vertex exactly once. And then along with this, you have Dirac's theorem, which states this, that if you consider a graph of 3 or more vertices, and no multiple edges, and you let n be the number of vertices if every vertex has a degree of at least n over 2, then the graph is Hamiltonian. Right. So again, you think in terms of, let's go back to my drawing I had earlier. We had this one. Let me just redraw this. And quickly draw this graph. So we had this graph, and I had it up earlier. So if I look at this, I have 1, 2, 3, 4. I have 5 vertices, so n is going to be 5, right? And so this says it'll be Hamiltonian if my degree, and so this case would be 5 over 2. And so this is going to give me 2.5, right? And so the question is this Hamiltonian or not? And in this case, the answer would be no. And again, if I relabel my vertices, we said this was A, B, C, D, E. And if you look at this, we have that vertex A is only second degree. And so we're not past that theorem. Right? But you get in terms of, again, what is called a weighted graph. Has an associated value with the edges. Right? So has an associated value with the edges. So if I had something like this, right? So let's say I have some cities. So A, B, C, And then I had some edges, A to B, B to D, A to C, and right. So basically what it would mean is that I would have an associated number with these. So let's say A to B is 400 miles. Oops. So this is 400 miles. Let's say A to C is 700. B to D is 550. And D to C is 300. So basically there would be an associated weight with those edges. In this case, mileage from one city to the next. Right? Right. So you get in terms of a couple of algorithms that go with this scenario. And so you get the first one called the greedy algorithm. And so you choose a vertex to start at, right? So you pick a starting point, first step, and then travel along a connected edge that has the smallest value. Okay. So we travel on an edge that has the smallest value, right? Next up, number 2. After arriving at the next vertex, so you get to your destination, travel along the edge. So now we go to our next, travel along the edge. That has the smallest weight. That has the smallest weight. That connects to a vertex not visited. And then you continue this process until all the vertices are visited. And then lastly, you return to the starting vertex. So you have, in terms of that algorithm, dealing with Hamiltonian graphs. And so there is another one variation on this one. And so the other one is the edge picking algorithm. So here, you mark the edge of the smallest weight. Right. So we mark that edge, okay, with the smallest weight. 2. And then you mark the edge of the next smallest weight as long as it does not complete a circuit. And does not add a third marked edge to a single vertex. And then the last step in this process is 3. You continue the process until you can no longer mark edges. And then mark the final edge that completes the Hamilton circuit. So we complete our circuit. All right. Well, other types of graphs they talk about in this chapter is you get a planar graph. It is a graph that can be drawn so that no edges cross. So if you think in terms, if I had this and I had it looking like this, well, that would not be planar because after all, 2 of my edges are crossing each other. Right? Right? So this is not planar. But if I change the drawing, and now draw it this way, and now it is planar. So there is a formula that goes with this, and so we have in terms of Euler's formula, which is this, in a connected planar graph, with no intersecting edges, let V be the number of vertices, E is the number of edges, and F is the number of faces. Okay. then we have this is true. Then V plus F equals E plus 2. So let's look at an example of this. So now I have this one. And draw in my edges. So yeah, here to here to here. This way. Okay. So vertices, we have 5. Okay. Edges, we have 7. Faces, well, there are 4. Okay. And so there are the 3 that are obviously you can see by the 3 sections, but then the 4th one is the whole entire picture. Right? So now, is this true? Well, we get that 5 plus 4. Does that equal 7 plus 2? So 9 equals 9. That is true. And so, yep, that works. Okay. And then the last section of this chapter deals with coloring a map. And that is every planar graph is 4 colorable. Which basically means that if you look in terms of a map of the United States, you'll probably see that the whole map is colored only using 4 colors. Right? And then a graph is 2 colorable if and only if it has no circuit, it has no circuits, of an odd number of vertices. And that will conclude this video.